because implicitly here I have decided I'm going to transmit to the legitimate user that reports the highest channel gain.
So you will back off from the...
I will back off here.
To achieve a certain outage.
Exactly. This is what I propose. But in order to be able to do that, we need to have already some good average, some good values for the expected secrecy capacity. So, yeah, this is pretty much the gist of it.
We're using the, we don't need, it seems the projector is fine.
Okay.
But the laptop is affected by Sandy.
Okay. All right. All right.
Okay, so looking now at the two scenarios side by side, we have the first scenario where we basically assume that our transmission occurs in the presence of k-1 eavesdropping terminals, and the second scenario where we reverse the situation, we have our transmission occurring in the presence of a single eavesdropper. And looking at the outage probabilities here, so if we are interested in transmitting half a bit per channel, then this can be achieved pretty much 20% of the time in the first scenario, and pretty much 90% of the time in the second scenario.
So the first one is there's k eavesdroppers, and k is the bottom axis, the x-axis.
Yes, k-1.
And this is there's the legitimate user is the one person with the best channel?
Yes,
or?
yes. So the legitimate user is the one with the best channel, and we have k-1 eavesdroppers, potential eavesdroppers.
And the thing you're plotting is the outage, the probability of an outage?
Yes.
And the outage event is the rate is...
When the rate is larger. Sorry, when the secrecy capacity is below this threshold tau.
Yeah, and what is tau?
Tau here is 0.5 is the red line. 0.8 bits is the green line, which is a bit curly because of the numerical evaluations. 0.3 and 0.1 bits. So for this case. And in this scenario, I start from 0.1 bits per channel, 0.5 bits per channel, 1 bit per channel, and 1.5 bits per channel. So basically it says here that I can transmit 1.5 bits per channel in perfect secrecy, 50% of the for 50% of the transmission frames. So if we're looking at not perfect secrecy in the sense we know it, but more in order like disrupting someone's reception in order to make his reception unusable, basically. So in video streaming, if we disrupt 50% of the frames, maybe the result is unusable. So if we're looking at this type of applications, maybe this is even a good situation. But if we look at what we know as secrecy, when we actually look at it, then we should be looking at those smaller rates. So it depends again on what we want to achieve. So you might argue that 90%, half a bit for 90% of the frames for 30 users in the presence of a single eavesdropper is not that high, but if we keep increasing the cell size, then these lines will actually...
Okay, let me understand this a bit. But the way, I guess, there are two ways of saying outage, right? Because an outage may mean you are guaranteeing a very, very small or tiny probability of incorrect reception at...
I'm talking about secrecy outage here. So
right, so that's what I'm aiming at. Is this purely what the secrecy outage is?
This is purely
and you can guarantee direct with the full probability, even though it's random? Or this is where you report the values, so you know what the chunk value is?
No, basically in order to evaluate the secrecy outage probabilities, we need to account for all possible channel gains in the two sets and evaluate the overall probability. So this is what we're doing here.
Okay, so you're saying to channel to Bob is not random? It's not.
No, the channel to Bob is random.
So how you have also outage there?
Yeah, that's a good approach. No, actually,
unless it's ergodic, unless he's either reporting or unless it's a ergodic channel and you
I average overall possible Bob gains as well.
Then you're looking at ergodic situation, but then it's not, in your case, ergodic situation. That means that if things change over many times, then all channels change, and who's the eavesdropper?
Yes, it's true, but I keep something which is constant. I don't care about who the instantaneous Bob is. My Bob changes from transmission frame to transmission frame, but this Bob, this Bob in each time frame will have the same probability density. The channel gain of this person will always have the same
That's fine.
period.
So somehow if you're coding over many Bobs, they somehow should combine this information in one place and code.
Yes.
Right?
Yes, I know.
Also, if somehow Bob and Eve change, sets, then you have to combine information between Bob and Eve.
It is true, yeah. Or maybe each Bob has to wait over a long period of transition frames until he gets enough symbols to decode. Okay, so yes, this is something that happens.
Yeah, just trying to understand the framework.
Yes. Okay. So the next thing we did, I'm sorry we're running really late here, is to look at now fiercer type of attacks. So up to now, our adversary was just passively intercepting the transmission channel. And now we're looking at stronger eavesdroppers, adversaries, which we call active eavesdroppers. And now these adversaries now are willing to take some action, okay, in order to confuse the base station to make a wrong decision. So now we're looking more at the scenario where we are actually interested in what each user is reporting. So in our setting, the eavesdropper appears as a subscribed user and uses false feedback in order to confuse the base station and make a wrong decision. And the aim of this adversary is to maximize the information that will be leaked. So if we think about it, a nearly optimal strategy for this type of adversary will be the following. If the adversary has the highest SNR, okay, so no legitimate user has a positive secrecy capacity. So the secrecy capacity is 0 for all users. In this case, this adversary will be interested in reporting a lower SNR and trying to convince the base station to transmit to somebody else so that this exchange of information will be transparent to it. Now, if it does not have the highest SNR, then it might not be able to eavesdrop. So in this case, if this is the goal of this adversary, to maximize the information leak, then it will try to block the transmission. Okay, so it will try to convince the base station that this is the best user in a given frame and be assigned the network resources. So this is our understanding of it. So in this case, we have no information leakage, but we have a waste of network resources. So the base station transmits to the eavesdropper in this setting. Okay, so in order to understand this much more complex situation, we started with the toy problem formulation. So the base station in our approach can only transmit to the user, to the terminal, let's call it this way, including the eavesdropper, that reports the highest SNR. And the second assumption we make is that the active eavesdropper always reports the fourth SNR value, gamma prime, which deviates from the actual value, gamma theta, by some quantity epsilon on the real axis. And we use game theoretic tools to approach this type of competitive interaction. So we have a common utility function here that is closely related to the secrecy capacity of the network, but also depends on the probability that the eavesdropper does not manage to confuse the base station, does not manage to convince the base station to take a bad action. So this whole game relies on the sign of this utility function. So if the sign of this utility function is positive, then the base station transmits to a legitimate user, and there is some non-zero secrecy capacity. If it is zero, the base station transmits to the eavesdropper, and we're wasting our power and resources. And if it is negative, then we have potential information leakage. Okay. So this is the game formulation. So the action of the base station is to choose whether to transmit at Pmax or not to transmit at all. And the eavesdropper has two actions. One, to over-report by epsilon upper hat the SNR, and the other is to under-report by some epsilon down hat the SNR. And we have here the more detailed depiction of the Nash equilibria according to the regions there. So
does it mean that the base station and the eavesdropper have the same utility functions? Right? So somehow the eavesdropper writes
The same form.
the same form. We formulated this this game as a zero-sum game. So
if
the amount one wins is the amount that the other person loses.
Okay.
So this is the apparently it can be much more complicated, but this was our first approach to it. Because in this case, we can always find a solution to the game. We know that there always exists an answer. So, and we all wanted to understand, to get an understanding of what goes on. So, the main observations we can make out is that the secrecy rate depends on the ability of the eavesdropper to over-report, so on epsilon upper hat. On the other hand, the information leakage depends on the ability of the eavesdropper to under-report, so of the epsilon down hat. And we say here that we can bound probably the epsilon upper hat if the reporting of the channel gains takes place through transmission of pilot symbols, so that the base station actually estimates the SNR. So we can never over-report this stuff, but we can still under-report the SNR if the eavesdropper pre-distorts the pilot symbol, so that it appears it has specific lower SNR than the actual SNR. Okay, so we believe that this case can be taken care of very easily, but this case here is much more challenging to see.
You can also change the transmit power of the pilot. It's not only power.
I'm sorry?
If you increase the transmit power, then what your normal transmit power is for the pilots.
Yes.
I guess that you spend more energy, right? But you can over-report.
Actually, if you increase the transmission power, we're going to see that you cannot over-report, really.
It depends on the knowledge of what your transmit power is by the base station, and basically the distance also. But
yeah, okay, you're right.
But I understand. Like, I'm just trying to understand your assumptions.
Okay.
Yeah.
Well, my basic assumption is that, in principle, we haven't really solved this problem, but in principle, we should be able to somehow restrict the ability of the eavesdropper to lie, or at least bound it.
Okay.
Okay, so this is the assumption we're working with. So the secrecy rate that is achievable given this formulation is given by this expression. There is a loss on the average achievable secrecy rate because of the action of the eavesdropper. And if we don't bound the epsilon upper hat, then this loss can be detrimental. We will have a zero achievable secrecy rate. So this is what we have here. However, if we let the transmission power increase unboundedly from bounded finite epsilon upper hat, then this normalization that will take place here over Pmax will actually make this term disappear. So we have a very interesting result that for bounded epsilon upper hat, the activeness or passiveness of the attack does not make any difference if we operate in a highly SNR regime. So for bounded limited systems, it doesn't really make any difference. Okay? So now looking at the numerical results here, the expected value of the secret and the standard deviation of the secrecy capacity in the high SNR regime in the presence of one passive or active eavesdropper. Looking at the results here, so for 100 users, we can achieve pretty much 3.15 bits per channel on average. We can transmit that much at a standard deviation of 1.88 bits. And the secrecy average probabilities here are much better. So for a small size network of 30 users, 93% of the time we can transmit half a bit in perfect secrecy, and 1 bit for 84% of the transmission frames. So this is the idea. And how we're going to use those results? Well, here we have just a snapshot of the possibilities. So the very simple heuristic approach of transmission policies. So the first one, the base station transmits at the best reported digit per user at a constant rate equal to the expected value minus the standard deviation of the secrecy capacity. So we're downplaying, and we can evaluate the information, the probability that information is being leaked. So we always assume that if the transmission rate exceeds the secrecy capacity, then the whole package is transparent. The whole symbol is transparent to the adversary. And in the second scenario, we take some extra cushion. So we use an extra safety cushion. So we also want here our best reported channel gain to be above what is expected from what is expected today. Otherwise, we don't transmit. So here we have a better chance to transmit in secrecy, in perfect secrecy. And looking at how those might work in real life. So for a small network, again, of 30 users, the constant transmission rate is pretty much 0.9 bits per channel, and the 14% of that rate would correspond to information to the rate of information leakage. So if this is too much for us, if we cannot tolerate this much amount of information leakage, then we could go to lower transmission rates, more conservative transmission policies. Okay, but this is the idea of how those things can be used in real life. This is the central idea. And what we're looking at is to design transmission policies based on threshold for the average rate of information leakage, and basically design the network, so make assumptions about the size of the network, given that we have an estimate of the number of eavesdroppers, taking into consideration throughput and secrecy constraints. How much is tolerable, if all, for the information leakage. And the second approach we want to look at is slightly different. So, for example, over a specific amount of time or over a specific number of transmission frames, okay, to place an upper bound on the amount of the information that might be leaked. Okay, so saying that in one day, if you transmit 3 gigs, I can guarantee that 2.8 of them are perfectly secure. So this type of thinking. And what we believe, I mean, in this whole presentation, I have no cooperation between anyone in the two sets of populations. So now if we also use this amount of cooperation, so for example, if we have 100 legitimate users cooperating and competing against 5 cooperating eavesdroppers, then what we normally should expect is that all those numbers will be further enhanced. So our opportunities for secret communications can be substantiated in this type of scenarios. Okay? Yeah, just the results. So we have looked at broadcast networks with passive eavesdroppers in the absence of any side information, and we have shown there that the secrecy capacity that rapidly decreases with the increase of the number of terminals. If some side information is available with respect to the number of eavesdroppers, then we can achieve substantial secrecy rates on average. now the active eavesdroppers represent a much fiercer type of attack, and the conclusion there is that for this type of attacks to be dealt with, we need to have a larger amount of side information. We need to understand the behavior of the adversary. Otherwise, there's nothing we can do against it. And a very interesting result, given the specific modeling of our adversary, was that if we operate in the higher scenario regime, then the network becomes insensitive to the activeness or the passiveness of the attack. And this is a very important result. So the gist of this is that as long as the legitimate users outnumber or have a better diversity, let's put it this way, okay, with respect to the eavesdroppers, then it is possible, actually, to design some reasonable transmission policies.